my work here. But yeah, I'm still not sure. Like, I mean, I have a general understanding of how, like, what it means to take. I mean, you're basically looking like for the gradient of L, with respect to that V matrix. But yeah, symbolically, I'm not sure how you would actually do that, and I couldn't really even find a good site for doing it. Because like, yeah, so that one you may have to if you want to figure that one out. Yeah, you might have to find like a math person to um, sort of take it from there. Um, but the other
Hmm.
stuff I don't think looks too bad now that I've had a second look at some of it.
Okay.
Um, okay, so I don't know. Did you have any particular place you wanted to pick up, or just wherever we can?
I mean, just the simplest one
Yeah. Um,
that we can work on.
okay, so I think let's see. So we worked up to 5, and then uh, I'm looking to see if I have. Do I have what? Oh yeah, I do have 6. Yeah, I think 6 shouldn't be too bad. I need to look up a couple of things to be sure about, but yeah, 6 and 7. Actually, 6, 7, and 8 don't look too bad, so maybe we can do those. So once
Sure.
again, I will pull this up on the board. I'll start with board 2 so that it doesn't download funny. All right, so here's number 6, I believe. Okay, so all right, so let's just kind of go through maybe and work out exactly what they're saying here. So we've got another convolutional neural net here. Um, and so maybe if we just kind of sketch out, let's see. So we have an input. I guess they don't say. Oh, okay. Yeah, yeah, they do say. So input, just to kind of like transcribe it again. Oops. It's like the wrong drawing tool. Input is 3 by 128 by 320, 128. So it's like an RGB image that's 128 by 128. All right, and then we have conv 932. So that's like they say, and they're just kind of introducing a weird notation, but so that's in filters. So that's okay. So that's k by k. So that's a 9 by 9, and I think we assumed last time that they mean. Let me put that first because they put their channels first. So 3 by 9 by 9. Um, and then we've got 32 filters. And they got, what is that? Padding is 0, stride is 1. Just abbreviate stride 1. So those are basically, the padding of 0 and stride of 1 are kind of the simplest parameters. So that should be easy enough to work with. Okay, and then we have a
Hmm.
pool 2. So I guess they don't really care whether that's like max pooling, min pooling, average pooling, whatever. But that's basically um, and I presume actually, yeah, they don't say this, so I'm going to assume. Hmm. I guess I'm going to assume that for their max pooling, because again, they don't, or their pooling layer in general, they don't really indicate this. I'm going to assume that pooling layer is 2-dimensional and leaves the number of channels intact. But that again is like something they don't really say explicitly that I would normally, if I were like writing the code, I would be explicit about that. Um, but I think that's kind of what they're getting at right now. So, all right, so that would be a 2 by 2. Well, it'd be 1 by 2 by 2. I'll put a question mark just to indicate that's kind of a guess. And that's padding is 0. Stride of 2. Okay, which makes sense. Okay, and then we've got con 564. Okay, so that'll be 3 by 5 by 5. Oops. And that's 64 filters. And pad of 0, stride of 1. Okay. Then we've got another pool 2. I won't repeat that one because it's the same thing again. And then we got another con 564. Okay, so that's the same thing again. Okay, and then another pool 2 last time. Okay, and then FC3. That's a fully connected layer with 3 neurons. Okay, so I'll say like 3 units. And okay, so for each layer, calculate the number of weights, number of biases, and the shape of the associated feature maps. Okay, yes. All right, so I think we got all the information kind of transcribed in a way that makes sense for that. Now, the only thing I need to look up for this, I think a convolutional, we don't really talk about the biases because you don't often talk about that too much for a convolutional layer. I'm not sure if the convolutional layer is assumed to. Okay. Yeah, I don't know what the convention is for the biases. I think it looks like, at least in a PyTorch context, oh, wait a minute. Okay, so yeah, so there's one bias for each output channel, it looks like, at least in PyTorch. Okay, let me double check that. Yeah, okay, I think that's right. So basically, yeah, that's what I would have sort of suspected. So one bias per filter or one bias per output channel. Okay. Okay, so that looks about like I suspected. All right, so we should be able to work this out. All right, so for a conv 932, I'll just repeat it again just to make sure. Well, actually, or I'll just here. I'll kind of maybe just do that. So put that up here. All right. So weights. All right. So the number of weights. If your filter is 3 by 9 by 9, that should be 3 times 9 times 9, which is the size of the filter. So that's 3 times 9 times 9 is 243. So let's see for weights. You multiply out your 3 times 9 times 9. And then your 243 you multiply by, you have 32 filters. So that would be 243 times 32. So that's 7776, it looks like. So that's total weights. Okay. So there's that. And so 32 biases. It's one per filter. Okay. All right. And the output, and then we need number of weights, number of biases, and the shape of the feature map. So basically the output shape. So the output shape. All right, so we worked out similar things to this before. So we said, all right, if the input's 3 by 128 by 128, there's no padding and a stride of 1. So since it's a 3 by 9 by 9, well, the output shape will be 32, because that's the number of filters, by, all right, so now for the 128, we would take off 8 on each side, I guess, of our filters 9 by 9. So it's going to be taking off a total of 16. So I think that's 32 by 112 by 112. Let me just double check that here. So yeah, it's 9 by 9. So you, on each side, you lose 9 minus 1. So it'll be 128 minus 8 is 120. 120 minus 8 is 112. Yeah, so if there's no padding and a stride of 1, should end up with 32 by 112 by 112. Okay, so that's your first layer. Is that making sense so far? Okay.
Yeah.
And filter. Okay, so weights, biases, and the feature maps. All right. So then we've got a pool 2 layer. Okay, so that has no, or I don't think that would typically have any. Yeah, like, because a pooling layer you typically do, like, calculate either a maximum, minimum, or an average or something like that. So so we'd have no weights or biases. There's nothing to fit there, I think, conventionally. Unless there's actually I should double check that in like PyTorch, because you said you guys were using PyTorch, right?
Yeah, but in code, so I don't know about.
Yeah, I mean, I don't think there's. Let me just double check, but my understanding is that I've used. Okay, that's what I thought. Yeah, like no weights or biases on a pooling layer. Yeah, okay. Just wanted to make sure that PyTorch didn't do anything weird in that respect, where it had optional ways to add stuff to those layers. All right, so no weights or biases. So then you're calculating, presumably, if we're assuming it's a 1 by 2 by 2, and the stride is 2. So basically that's going to cut the dimensionality in half in each of those dimensions. Right, so that's going to be, so weights and biases. So output shape. Oh, actually, this is interesting. I have to think about this. Hmm. Well, we'll have to worry about this in a minute. Um, the output shape is going to presumably be 32 by, I think that will be 56 by 56. Okay, now this I didn't really think about, but I guess if they're not specifying, I guess actually this next one for this convolutional, it's just weird to me that they don't like. Let me see how PyTorch defines their like convolutional layers. Um, yeah, because like before I think we were just sort of assuming that if you get a three-dimensional like a RGB input, you get an RGB output. Here, I'm no longer assuming that necessarily. Um, hmm. Yeah, because I'm not used to seeing people eliminate the sort of depth dimension. Hmm.
Mm.
Yeah, I mean, I guess. Okay, I'm seeing something. Let's see if this is right. Okay, yeah, I think they're saying that this would use all the input channels no matter. Hmm. Oh wait, maybe they're. Yeah, PyTorch might also treat these differently than I'm used to. Um, yeah, okay, this is actually a little bit of a difference in how PyTorch notates stuff. Um, so I think they're using a two-dimensional. I think they're using a two-dimensional convolutional layer to work on what I would consider a three-dimensional structure, but okay. Let's see. Okay, yeah. Okay, so I think, I mean, it doesn't really matter too much how we notate it, but I think we're assuming yeah, that this that this actually, all right, let me hmm. Yeah, I'm just looking at how PyTorch calculates their dimensions because it's actually a little bit different than what I'm used to using TensorFlow or Keras. So let me just see. How they work out the number of parameters here. Hmm. Okay. Just take a look here. Huh. Well, let me just try to look this up one more way. Okay. It's surprising how like little documented this is. And it's easy to calculate for like linear or fully connected layers. Um, Especially because they use sort of an um, odd way of doing it relative to the way I'm used to doing it. Okay, yeah, so okay, yeah, so this I finally found a page that kind of confirms my suspicion is that yeah, you just it works, works like PyTorch calls what I would call a three-dimensional convolution. It calls it a two-dimensional convolution with three channels or whatever, but it works the same way otherwise. Um, okay.
Do you have the link?
Yeah. Here, I'll share it and also kind of show you what I'm talking about. Give me one second to
Sure.
configure my screen for sharing here. Just to turn down the resolution a little bit. Okay. Yeah. So here's what I was looking at, and I mean, I'm assuming this guy, whoever it is, knows what they're talking about, or whoever this person is. Yeah,
Hmm.
but basically, yeah. So they're setting up um, PyTorch model. They're using like color images here, 3 by 32 by 32, and they're saying basically for the convolutional layers, yeah, that they're multiplying the width and height, or to get the learnable parameters, width by height by the previous layer's filters, and then by the number of filters in the current layer. So basically, this is sort of saying that yeah, you're going to have like that each filter is going to be width by height by the number of channels, essentially, which is basically what I thought. Just wanted, but it's I would call this a 3D convolutional layer, but they call it a 2D convolutional layer with channels, which is it's fine. It's just a little bit odd because it's really no different than the 3D convolutional layer.
Hmm.
Okay, so yeah, so that's pretty much just confirming what I thought. But all right, so
Okay.
then what that would mean, right, is that so actually what that would mean is that here I'll do this in different, so that your con5 is not going to be 3 by 5 by 5. It's going to be whatever the previous layer's output shape is, or output channels is by 5 by 5, which is going to be, I believe, 32 by 5 by 5, because that's how many channels we ended up with in the previous layer, I think. Again, assuming that our assumption about the pooling layer is correct. Actually, while I'm checking, let me just double check. How a pooling layer on PyTorch is supposed to handle channels. Hmm. Okay, yeah, I think I think pooling in PyTorch does not by default go across channels. So yes, I've got that confirmed. That's good. Um, pooling layer pools each input channel separately rather than summing the inputs over channels in a convolutional layer. Output channels for pooling layers the same number as input channels. Okay, that's just good to check. I'll link that page too. That confirms kind of what I was already suspecting. Okay.
Okay.
All right. So getting back here, then I think that means everything we've done so far is right. Once we change the number of channels in the con 564 to 32, so that would mean the weights would be uh, 32. Oops. 32 by 5 by 5. That's the weights per channel or per filter. So that's 800. And then 800 times 64 filters. is whatever 64 times 800 is. 51,200. Okay. And then that's going to be, let's see. So then we've got 64 biases. Again, one per filter. Okay, and that's going to mean the output shape is, so that's going to come out to be 64 channels. Okay, so we have no padding and a stride of 1. And so it's a 5x5 filter, and the input shape was 56 by 56. So we're going to lose 4 on each end of each dimension. That's 52. So I think that's going to be 64 by 48 by 48, right? So 56 minus 4, 52 minus 4 is 48. Yeah. Okay. So I think that's good. Okay. All right. So here, let me put some little separators or something between these sections. All right. So here's, this is all conv, and then this is for the pool 2. All right, and then this is all the next conv. Okay. Okay. So then I think we're ready for another pooling layer. All right, so another pool 2. So again, no weights biases, because nothing trainable in a pooling layer. And then the output shape would be, all right, so that should just, if it's a pool 2, it should just cut everything. And if it's pool 2 with no padding and a stride of 2, that is, it should basically just cut the sort of width and height dimensions in half. So that would go from 64, 48, 48 to 64 by 24 by 24. Okay, so that's that. This is getting kind of hard to keep these straight, so do that. All right, and then that's all of our pooling layer. Okay, and then another convolutional layer. So another 564. So this will be weights will be, let's see. Yeah, so it's 64 because it's the input channels times 5 by 5. Oops. 5 by 5. And so that's 64 times 25. So that should be 1600, I think. Yeah. So that's 1600 for like each filter. Should maybe put per filter or per, just to make that clear. I mean, that would apply to all the previous convolutional channels. All right, and then 1600 times 64 filters equals, so it'd be twice what the last one was. So that's 102,400, I think. 102,400, yeah. Total weights. Okay, and then, all right, so again, you'd have 64 biases by the same logic as before. And so that's going to be the output shape. So that's going to be 64 by, all right. And so the input shape was 24 by 24. Then we're using a 5 by 5 with a stride of 1 and a padding of 0. So we're going to lose 8 in each dimension. So that should give us 16 by 16. By 16 by 16. Yeah, that should be right. Okay. All right, and let's see here. All right, I'm starting to run out of horizontal space, so I'll go. I think I can go further to the right. So you might have to scroll around. Sorry. All right, so that's going to be. We're almost done though, so that's good. So that's going to be the convolutional 564. Put that in red just to be clear. That's our convolutional. Okay. And then going back up to the top on the right. All right, so our pool 2, say our last pool 2. Okay, so for pool 2, again, no weights biases, because those don't have weights and biases. And let's see, that means the output shape will just be, let's see. All right, so we'll keep the same number of channels, so that's 64 still. And then we're cutting, let's see, we're cutting, the other 2 dimensions in half. So that's going to be, what was it? We had 64 by 16 by 16. So now we'll have 64 by 8 by 8. And then our final FC3. So we'll have to this is implicit, but I think in TensorFlow, you'd have a flattening layer explicitly. PyTorch might do it automatically. So we'd have 64 by 8 by 8 inputs. And so if you multiply that out, that's 64 times 8 times 8 is 4,096 inputs. So you kind of flatten those and just treat them as like one long line of inputs. And you got 3 units, so 4,096 times 3 units equals, is that 12,288 weights, I think. Okay. And I guess you just have one bias for every unit, so that would be 3 biases. One per unit or neuron. And I mean, I guess the final output shape would be 1 by 3 or 3 by 1, however you want to say it. I guess I'd say 3 by 1 or whatever. Okay. Or actually, I think probably to keep it, let me think about this. Maybe you'd say 1 by 3 to keep it kind of in the same way that you notate the X inputs. Okay. So I think that's it. It's a little bit of a process for that one. I mean, it's conceptually not that difficult, but yeah. Where weights, number of biases shape the feature maps. I'll just put this is AKA output shape for each layer, because I think I was just calling it output shape. Shape the inputs 3 by 128 by 128. Okay. So I think we got that all right. Does that all kind of make sense?
Yeah.
Here, I'll do my little divisions here. All right. So I think that's got it all right. I mean, the numbers work out kind of nicely, so I think that should make sense. Any other questions or thoughts on that one, or want to just kind of keep going?
No.
Okay.
We can just keep going.
All right. So let's see. So that was number 6. Okay. So number 7. Yeah, I think these shouldn't be too bad. We'll just have to do a little bit looking up. We might be able to do 7 and 8. These are a little bit simpler. So you had 7 and 8 together. So we might be able to do those together on the same board here. Let's see. So I'll put that on board 3, just the image of the questions. We'll see how that goes. Okay, so all right, so we need to draw a diagram of an RNN for regression. Yeah, I don't know what this whole regression is all about. Having 2 inputs, hidden state of dimensions 2 and 3. Or sorry, hidden state of dimension 3 and 2 outputs. I assume all we're missing there is the word the activation function for the hidden state is ReLU. Okay. Okay, so write the equations for 2 times step 4. But the equations might be a little bit tricky. I forget, did you say they gave you like notes or like slides on any of this stuff, or not really?
I mean, they would. It would just be theory. We don't have anything worked out. I mean, I can pull it up if you want, but
maybe, yeah. I mean, for some of the equation stuff, it might end up being helpful. I'm not totally sure yet. Okay. Actually, maybe we'll do number 8 first, because that might be a little bit easier.
Did you want me to pull up something?
I mean, not at the moment, I guess, but if you have,
okay,
if you have it, if you see anything that you think would be helpful, feel free. Because some of these, I don't know off the top of my head like the equations for, 4 passes through RNN. So I don't know if they gave you notes on that stuff. Calculating the number of parameters of an LSTM. That's something I'll have to look up a little bit. But I think that should be fairly straightforward. Let's see here.
That's 7 and
Okay.
8, so it should be towards the end of the notes, I think.
Yeah. Okay, so number of examples is n, number of inputs is d, and the number of hidden units. Hmm.
So that's helpful.
Number of inputs is d. Hmm. Actually,
Okay, so I don't have anything for LTSM or whatever that's called.
yeah, LSTM stands for long short-term memory. That one I think is more straightforward. The RNN equations I'm a little bit less clear on. Um,
Yeah, so nothing.
Actually, I mean, the one thing they use such odd terminology in here. Um, so I think they're saying the number of
Which is probably because it's translated most likely.
yeah, and I mean people do use even without language issues like people do use like lots of different terminology and like if you use one software framework sometimes people talk about things differently than other software frameworks. But I think so I
Mm-hmm.
think what they're saying is the number of input units is D. The thing that I'm not sure, they're saying the number of examples. I'm not sure what they mean honestly by. Like usually you mean examples to talk about like the size of the input data. Um, and LCM layer. But examples, number of inputs. I mean, I think I have to interpret that to mean like. Well, actually, let me go on to LSTM network here. Hmm. Hmm. Number of hidden units is 3. Yeah, the number of examples is tricky. Let me just take it. I mean, I've got some places with like equations for this stuff. I'm just kind of working through translating the terminology and making sure. Hmm. And oh. Yeah, like the input length does not. Okay, I mean, yeah, the, the number of inputs shouldn't really matter because the LSTM unit is the same regardless of the input. So I think we can ignore the input and just look at the number of hidden units. And I guess that leaves, yeah, what this, doc, I'll share this page with you in just a second here. Um, hmm. I'm just missing where they define one of their variables here, which is kind of important. Hmm. For examples is N, number of inputs is D. Maybe by, okay. I think I see what they're getting at here. So the thing that I'm not, okay, so maybe it's actually when they're talking about this, I think we're talking about, let's see. So I guess if they're saying number of examples, I guess that's the one that doesn't matter here. I'll send you this page. But I think what they're saying, if I understand this correctly, I think if I get it, so from that page here, I'll copy this conclusion from the page. And I'll double check this formula somewhere else, but here, let's see. So this is for Q8 here. Okay, so I think if I understand this correctly, I'm interpreting this to mean size of each input each time, like, because we usually think of like LSTMs as operating across time, so like each time step or something like that. I think they say number of examples. I think they're saying number of time steps. I think that's a little bit of a question mark. And then the number of hidden units is fine. That's H. So here in this expression, H is H. It's the same as in the question. And here I think the X if I'm understanding the terminology right, so that's the size of each time steps input. Which would make this, so that would be 4 times D plus H times H plus H, which equals 4 times yeah, so doing the numeric application, that would be 4 times D is 3 plus 4 times 4 plus 4, which would equal 4 times 28 plus 4, which equals 4 times 32, which would be 128. So I think that's right. Let me just like look at a couple of other references. And make sure that agrees with other people's. Oh, actually, well, does that work out the same algebraically? 4 times. Okay, yeah, that works out the same. Here's a stack or stack exchange on the same thing. Of course, everyone uses different like letters and notation for this stuff, but they call them N for yeah, N I guess for the number of. They don't really describe it very well. They call it nm plus n squared plus n. So that'd be like dh plus h squared plus h. Yeah, so that would be the same thing, just using different variable names. Okay, so that looks correct. Yeah, the only thing I'm a little bit unsure on is translating what they're calling examples and inputs, but I think, as I understand the terminology, that's what they mean. Okay, so does that part kind of make sense, or
Yeah.
not really?
Yeah.
Okay. Yeah. Okay.
I would have to look at because I recorded my lessons,
Okay.
but I don't remember if we solved anything in class. But I don't think we did because I would have had screenshots of it. But it doesn't
Okay.
hurt to check.
Yeah, I mean, yeah, the more practical stuff I feel like we can work out from general references. I'm a little, some of the theory stuff is a little bit harder, but
Yeah. For some reason, I remember the D plus H. I might be remembering from a different class, but
yeah.
for some reason, I remember this formula from somewhere.
Okay. Yeah, I think. Yeah, I mean, yeah, I think the formula should be right. I mean, you could write this.
Yeah.
So you could write this also as 4 times dh plus h squared plus h or something like that. If you wanted to. But yeah, assuming I've got those, like assuming I've translated, those n's, d's, and h's, or what they mean by the number of examples, number of inputs, number of hidden units is fine. That seems that part seems fine. It's just making sure I understand when they say the number of examples or the number of inputs. Like, for a number of inputs, I'd probably say something like the number of values in each input or something. But I think that's what they're getting at. So I think that's right. And it does lead to like kind of a reasonable looking number. So, yeah. Okay. All right. So that's that one. And then maybe we can do maybe I'll just make another copy of that same image because we've used up a lot of this board. So let me copy that image again and paste it for board 4. We'll see if we can get through the RNN. Okay, so so the diagram of an RNN for regression having 2 inputs, hidden states of dimension 3 and 2 outputs. Boy, this is all right. So I guess this is just a basic. Let's see, hidden state of dimension 3 and 2 outputs. Okay. So I guess you have a recurrent layer activation function for the hidden state. All right. Let me see. Do you know what, like, have they shown you any like diagrams for these recurrent neural networks?
Let me just check.
Yeah, I'll see if I can find like a good diagram to kind of crib from in the meantime. Because I guess they're talking about like a basic,
It is something, but I don't know if it's enough. There's like a little formula. Where is it?
Sure. Now that may be useful for, let's see. Let me just make a quick little temporary screenshot of this. Okay. Yeah. Okay. So that may be useful later. But they didn't show a diagram of those networks, or did they?
I think this is the only one that I have.
Okay. Oh, wait a minute.
But I mean, I can go.
Wait a minute. This might be. Well, let's see. I'm just looking at. That's an unrolled neural node. Let's see. Let me. That might be kind of the sort of diagram they're looking for. Let me just. We're going to have 2 inputs, a hidden state of dimension 3, and 2 outputs. Yeah, I mean, maybe. Do they? Yeah, if you go up a slide, do they have any other diagrams or any other figures?
I can go down.
I think it would be higher
But
up,
that
if
don't have a-
anything.
Would this one be it?
Okay. Yeah, maybe. What's that? Well,
Let me just do this thing on because I think I know what you're saying now.
Yeah, but I was wondering if they had a more basic one, like earlier in the slides, because this is more of like a specific example. Okay, so like figure 1, that's nothing. Okay, so well, okay, yeah. So I guess figure 2 is just yeah. That's a well. I mean, maybe that is what they're getting at. Let's see. So they want 2 inputs in state of dimension 3. And 2 outputs. Oh. Okay, wait, can you go back to the figure 3 again? I'm just trying to figure out which, I mean, these all kind of look alike. I'm just trying to sort of figure out what they might be wanting for that figure. Okay. So, yeah, because they're going to be producing. Hidden state of dimension 3 and 2 outputs. Yeah. Hmm. Okay. Hmm. Yeah, so I guess we would use something like that, I think. Yeah, I mean, in this case, we'd only have like um, 2, I guess 2 inputs and 2 outputs. But yeah, I guess that's probably what they're looking at. So, or looking for. So, yeah, all right. So we could probably replicate pretty much this figure 3 for the
Mm-hmm.
question. So here I'll paste that in on the whiteboard also next to the question, and then we basically do a cut down version. I think that's probably what they're looking for. Oops. There's a lot of ways you could draw these diagrams, but I think I get what they're saying. Here, I'll make that kind of small so that we can draw a bigger version below. Okay. So basically, if you wanted to do 2 inputs, the hidden state of dimension 3, I guess that part, um, that's the only part that's giving me a little bit of trouble, but I guess we don't. Let's see. I'm just looking to see like how other people draw these hidden states when they've got multiple things inside them. Because yeah, I guess that's only sort of showing one hidden state in a way. Yeah, there's so many different ways to draw these things. They're saying RNN progression have 2 inputs, hidden state of dimension 3, and 2 outputs. Yeah, the dimension 3 is the part that's giving me a little bit of trouble. Uh, especially because the length is only. Yeah, the hidden state of dimension 3 is a bit. I guess they're just saying that there's three units. Let me see how they've got this. Yeah, so I think let me grab the link for this one. I think they're kind of thinking of something like this. Yeah, okay, so I think probably this is the sort of diagram. I'll post the, or I'll send you the link and also put the figure on here. So I think they're probably thinking of something like this figure. So this is where it gets tricky is there's like, well, as this guy kind of conveniently explains, there's like what we call this like shorthand notation and then what we call the unfolded notation. So they're showing kind of like an unfolded notation, but they're only showing it for like one input. But basically, I think you could just, like stack up multiple units to get an output. So I think what you draw would then be something like this, I guess. So you'd have like your X, we'll call it like X0 or whatever. And that goes into a hidden layer with 3 units. Maybe call that, let's see, I think those are, I always forget, I think those are fees, if I remember correctly, fees or phis, whatever you want to call them. I'm bad with my Greek letters, but I think that's what you use. Actually,
I think that's what I call it.
Yeah, I was going to say,
Yeah.
I have like flashcards because I've been practicing my Greek letters because every once in a while it comes up. But yes, I think that's that one. But anyway, so, 0 and 1 and 2, if we're using that notation for the, that other blog was just using A's or whatever. But yeah, if they're using fees, then that's fine. Okay, so then let's see what you'd have. Okay, so then you'd have, basically your first output. Well, yeah, I guess this would be pretty straightforward, right? Then you'd have your first output, which would be your, I would probably call this, like my Y0 or whatever. So this is input, hidden, and outputs. And then, so you'd have 2 inputs. So you'd have another hidden here with, again, phi 0, phi 1, phi 2, x1 goes in here. And then that would produce y1. And I guess, let's see, hidden stated dimension. Got 2 inputs, hidden stated dimension 3, and 2 outputs. The activation for the hidden state is ReLU. Okay. Yeah, so the equations, I'm not sure that I'll be able to generate unless you have. Oh, yeah. Let's see. Let me see what they had for. Yeah, paste that in somewhere and just double check what they had for equations because that might be useful. Actually, I'll just paste that on the whiteboard here. Let's see. Oh, actually, that pasted somewhere else, but that's all right. They said what did they say they gave? They said write the equation for 2 times steps of forward pass through the network. Yeah. Oh, you still there?
Sorry about that. I accidentally hit the back button.
No, that's all right. I just want to make sure I didn't lose you for good. Okay. Yeah, so that equation that they was on that one of your slides looks sort of relevant, but doesn't look like totally.
Let me just let's see.
Yeah.
This one?
Yeah, that one. Yeah. Yeah, so yeah, it's a little bit weird because that makes sense for like a single recurrent unit. I mean that's really like the okay, yeah, looking at this, like the hidden layers output is just phi is the activation function. That's just x times weights plus biases, which is like any kind of dense layer does the same thing. So that's not like super surprising. I'm just looking through. Just looking through some of these other equations from that page I linked. Hmm. just looking for like other useful equations for this stuff. Yeah, how do they say it exactly in the question? Write the equations for 2 time steps of 4 pass through the network. Yeah, I mean, again, there's stuff that's implicit here that if it's 2 outputs, when I say 2 outputs, I guess actually that would be, yeah. Hmm. Okay, actually, I guess I should have labeled these X. While I'm looking at this, I should have labeled these probably X1 and X2 because that's following. Here, actually, I guess, and they're calling their outputs. Let me just actually relabel all these things because I guess while I'm looking at this, may as well. Because it looks like they're labeling everything starting at 1, so we can do the same. So it'd be X1 and X2. Well, wait a minute. Let me think about this. There's so much that's so much that's like a little bit vague here. Because let me finish writing these in. Let me think about this a little bit more. Yeah, because when they just say inputs and outputs, I mean, I thought this was going to be straightforward, but now the more I think about it, I'm like, okay. So when they talk about the number of inputs, I think they're talking about, I think we decided that probably they're talking about the dimensionality of the input. What are they trying to say here? Because like usually you talk about these recurrent neural nets as processing a signal over time. And of course you can train them on multiple inputs or run multiple inputs through them. So I guess what I'm assuming they're notating here I'm not sure about this, but I guess I think what I'm assuming, although it's a little bit weird is I guess they're treating. I guess they're treating. So let's if we like look at this. Let me just leave some space here. 1, 0, 1, -1. I think what they're implying is that like this is T1 and this is time point 2. And I guess what they're saying is run both of those inputs all the way through the network and compute the outputs, compute both outputs for both X's. That's the best I'm able to work out. Now, let's see, how would that work? So each of those little fees or phi's is it basically acts like a fully connected unit individually. So you should, I believe, get a vector. Yeah, you should get a vector out of each. Well, let's see their output. You see, they say that it's 2 outputs, but I just don't know when they say 2 outputs, if they mean like outputs for 2 time points. I guess they do. Or maybe not. You know, that's what I'm unsure about. And I'm also unsure, like, but yeah, since you've got like 3, you know, I mean, you could do this various ways. I don't know if they're like, all right, so just here, let me share this other, this post that I shared just to kind of, you know, it's like there's just so much left unspecified. You know, here what this guy's talking about, if you look at this like architecture diagram, you know, you have your inputs at each time point come in at T1, T2, T3. You know, that gets run and you get a vector of outputs, like the WYs are the vector of the outputs. Or sorry, well, the WYs are the weights, but you get a vector of outputs and then they're weighted. And your Y, actually, let me think about that for a second. Let me see what they're assuming their Y is here. Right. So I think they're saying right. Okay. Yeah, they're saying that they would have a like each Y would be a vector, where what they're doing is a softmax, meaning like, you know, they're producing a single prediction at each output, but that's because they're, you know, in this example they have like 4 letters DOGS, and they're kind of encoding those letters as like ones or zeros. So each output Y, yeah, would be like you'd have 4 sort of output neurons, but then you do a softmax over them to get your final answer. So when they say output here, I don't know if that's what they're getting at, or if they're assuming you would also do like a softmax. I guess maybe not. I guess in your example, they're saying there's 2 outputs, so maybe they just mean this is what I just don't get. It's like, is it 2 outputs at each time step? Like, because basically with recurrent neural nets, you can generate the output at each time step, or you can only generate the final output. And I don't know which they're talking about. So maybe they're only talking about maybe they only want the final output and they want both values. It's unclear. So yeah, like it. So in other words, like for this to kind of work out, you'd have to have each output would itself be. It's 2 outputs. I guess it doesn't hurt to show what the output would be at each time step. I'm just not sure if they're calling like these output 1 and output 2, because like each of these would themselves be 2 values.
Right.
Or at least I presume, if I understand what they're getting at correctly. It's just a little unclear because there's like so many things you could do with this. All right. Well, if we stick with this, and this is once again one that's like computing it would be kind of a chore. But we can do it because what you do is you'd do your X inputs. Let me think about this. Yeah, you do your X inputs. Actually, here, let me do it this way. Let me just notate this slightly differently again, because I think what they're calling X1 and X2, I think are like 2 totally different sets of input. And this would be like, X of T 0. Actually, I should have made that smaller to make it a subscript. So X of T 0 and X of T 1. So I think then, so you basically, this would be like, 2 values, and then you get 2 values for each of your hidden units. You'd have to have like a weight matrix of, what would that be? Like 2 by 3, or 2 by 3. That would produce 3, and then, well, those would get ReLU'd, but then you'd have a 1 by 3 output, and presumably those would go through weights also. Yeah, those would go through weights also to get to the output, and then the question is, what do we call the output? But let me take one more look at your. Yeah, I mean, that seems to agree with the way that, let's see. Yeah, that agrees with their equations that they gave. They just don't really kind of say what to do with the output. All right. So if we were to work through that, I mean, I think, you'd have to kind of, let's just pick some values. So let's just say like, all right, so you've got your hidden weights. So let's say, I think they were calling this like your hidden weights would be, or they noted that I think weights from X to H. So we can just make some up, right? So your X's should be 2. So we said that should be 2 by 3. So whatever, we can just do 1, 0, -1, -1, 1, 0, or something like that. And then you're also going to need, and then biases, I guess. I can just say whatever, -1, 1, 1, why not? And then, they don't really say, compute the outputs O1 and O2 of the network. Yeah, because I mean, presumably, if the hidden state has dimension 3 and 2 outputs. Unless they mean, unless they just mean, again, there's so many things you can do with these like outputs of your hidden layers, unless they don't want you to do any further. There's just so much guessing what they're wanting you to do, unless they don't want you to do any further processing, because they say the weight matrices. Well, they say weight matrices and bias vector. So that's as if there's more than one weight matrix.
Mm-hmm.
Although that would also imply you'd have more than one bias vector. So, yeah, and it's not clear what the activation, yeah, so much left unknown. But I guess you have to assume that what they want is that you want weights from hidden to output as well. So that if you're getting 3 outputs from your hidden layer, that would be then, and you're producing 2 outputs, so you need I guess that'd be a 3 by 2 weight matrix in that case. So let's say like, I don't know, 1, -1, -1, 1, 0, -1, something like that. And then biases for your output be something like, I don't know, what do we do here? Let's say 1, 0. Okay, so you could work that out then, I guess. So here, again, this is kind of annoying to do by hand with all the matrix math. So maybe we could do it like, with a tool first and then do it by hand if, like figure it out, confirm it by hand or whatever. Okay, so here, let me fire up a MATLAB maybe, and we can make sure we've done this right. And I don't know, so much guessing involved.
Yeah, so no explanations. Yeah.
Yeah.
There's no explanations, I guess.
Something like what they're looking for, yeah. but you know, this will generate something. It's just whether it'll generate exactly what they're asking for. Okay, so you know, here I'll share my screen again. Let's put in some values here and see what we can do. Oh, I can close this now, I think. All right, so why don't I? Oh yeah, I'll need to copy it. Let's see if I can get this in MATLAB onto the screen at the same time. Okay, so basically, let's say like x time, if I'm interpreting this right, x1 time 1 would be 1 and 0. And then x1 time 2 would also be, what it would be 1 and -1. If I'm reading that right. And then we sort of made up the weights from x to h to be 1, 0, -1, and -1, 1, 0. And the biases at that step we said could be -1, 1, 1. Oops. Okay, and then the weights from the hidden to the output could be something like 1, -1, -1, 1, 0, -1. And the biases for the output could be something like 1 and 0. Oops. Okay. All right. So I think that's all we would need. Okay. So then to get so basically like, yeah, so to get like hidden, let's say, yeah, hidden for x, for our first x at our first time point, that would be x1 at time 1 times wxh plus bh. Okay. And then the activation function would be ReLU, which would make anything less than 0 to 0, but we don't have to worry about that. So because nothing's less than 0 here. So let's say, so hidden that's 0, 1, 0. Okay, and then if we want to get our outputs as I understand them, so that would be hidden x1 t1 times who plus bo. Oh, I should set that equal to something. So that would be output 1 x1 okay, so that would be, oh, and then I realized there's something else we haven't put in yet. So output, oops. Output, right, I'll just say 01 because I guess that's what we're calling it. 01 for x1. We think that's a 0, 1, which again, well, that doesn't have an activation function, so I guess that's it. Now, let's get output 1. Now, to get our second set of outputs, we're going to need to compute our second hidden state. And let's see, did I close this? Yeah, we're also going to need weights. Yeah, weights from our hidden state to our hidden state. And let me just take a look here. So okay. I just want to get to the time point. Thank you. Time point 2 here. If they don't really get into that. Okay. Yeah, what I'm looking for is basically so you get like an output from the hidden state. All right, zeroth H vector will also always start as a vector of zeros. What I'm not sure about, let's see. Okay, yeah. So WH, so the weights of the hidden vector. So I guess that is assumed to be, yeah. So I guess that I don't see why it wouldn't be. Yeah, I guess each output can affect each unit of that hidden state. So I think that would be, so we also need to basically make up a weight matrix. Let's see, the hidden nodes are previous, weight by the weight matrix WH, the input X. Yeah, so I believe we just, yes. Yeah, we just add together. They say concatenation, but that's not really a good way to say it. It's a summation. Yeah, so yes, the weight matrix for the hidden nodes is D by D, where D is the number of hidden nodes. Yeah, so that makes sense. And then, yeah, so you're adding that to WX times XT. All right, yeah. So, right, so that should end up with D by 1 in both cases. All right. Yeah, so what we also need to make up then is, here we go. We also need to make up, I'll have to do this out to the side. We'll have to make up a weight matrix of hidden to hidden. So that would have to be, if there's 3 hidden states, that would have to be 3 by 3. Let's just do 0, -1, 1, 1, 0, -1, -1, 0. Why not? Okay, so you have to make that up too. So that'd be W over on MATLAB. That'd be, oh, why is that not working? Come on, MATLAB. Why is MATLAB hanging on me? Yeah, that's annoying. Weird. Oh, there it goes. Okay, I don't know why I was doing that. All right, so WH we can say is equal to 0, -1, 1, 1, 0, -1, and -1, 1, 0. Okay. So we make that up. All right. So then if we want to get our, scrolling back here, if we want to get our second hidden state result, so that's going to be hidden, it'd still be X1, but for T2. Oh, wait a minute, sorry. I did the wrong thing. All right, so hidden x1 time 2 is going to be x1 at time 2 times wxh. So that's still good. We need to add in hidden from time 1 times wh. So that's your previous time step times your hidden weights, and then still add your biases. So I think that's right. X1 from time 2 times the weights from x to h plus hidden, the previous hidden state times the hidden weights plus your biases. Right, so that should give you 2, 0, negative 1. And then if we say hidden x1 t2 less than 0 equals 0. So basically a little 0 at the negative 1. Oops. So that would give you hidden my tablet here is not loving this. X1 times 2 equals, starts as 2, 0, negative 1, but then becomes, by virtue of the ReLU, becomes a 2, 0, 0. Okay. And then if we want our output, so our output 2 for x1 would be hidden for x1 at time 2 times the weights from the hidden to the output plus the bias of the outputs. So that'd be 3, negative 2. So O2 for x1 I mean, then you could threshold that or do a softmax on it or something, depending on what you're actually trying to do with this RNN. But that would be kind of the raw output for an output layer, I guess. Okay, so I don't know if that made a whole ton of sense to you, but I mean that would let us work through. I mean that lets us work through my best guess as to what they're doing here for like one of the x's. That's as far as I can understand it. I mean, there's lots of stuff where we made guesses about what they meant. So I'm not 100% confident in all that stuff, but I mean, I think that's my best guess as to what they're trying to say here. Yeah. But it's a little bit unclear. So I don't know how much sense that made to you, or if you have questions or anything like that about that so far. Did I lose you?
I'm still here.
Okay, yeah. So I don't know. Does that sort of make sense to you? Any questions or thoughts on that so far?
No.
Okay.
I think that's pretty much it.
Yeah, I mean, so right. So, go ahead.
I mean, we all tried to ask. He didn't answer, so yeah. Like literally all of us tried to ask on all of these questions, but he refused to answer, so
okay.
It is what it is.
Yeah. Okay. Well, unfortunately, we're close to being at our time, and I do have somebody else in a little while.
Yeah.
I mean, I don't have to run exactly at this moment, but probably don't have time for a long one after this. So on this one, I mean, yeah, like, I guess, I mean, now that we've kind of worked through what we think it is, I guess we could write out equations for this stuff. I'm still not like totally sure what form they want that in, but we just did a process, so we could certainly write equations for that process. Um, for and like for the rest of this question, we did it, with the assistance of MATLAB for X1. I mean, we still could do it for X2 and doing it by hand. So I don't know where you want to spend your time, or we could just go on to another question. But that's all a little bit academic because I guess, we're close to out of time, but
Yeah.
that's
So
got
I was
most of this one done, but there's definitely some stuff left in this one too.
okay. Yeah. I was thinking this is a good stopping point. And our
Yeah.
next lesson, hopefully we finish 8 and 9. I mean 9 and 10. Do you think we'll be able to finish in 1 hour?
Let me take a look at. So let's see, 9 and 10. Yeah, let's talk
I'm
about
gonna
that.
schedule 2, but I want to keep the second hour for maybe if we have to finish stuff or
Yeah.
whatever.
So let's see, 9 and 10. Right. We're the ones about additive attention, and then the thing about the flops, right?
Yes.
Which for the what is this? The multi-head self-attention. So that stuff I still don't know a whole lot about. Do you have any like slides or anything on the attention stuff? Because I'm sort of vaguely aware of the topic of attention, and I looked into it a little bit the other day. I didn't have time to get super deep into it.
I haven't
But
found any. I mean, unless there's another term for it. I don't remember if we have any. Let me just share my
maybe actually,
screen.
if you have a minute, I don't have to go right away. Maybe if we take a look through what you've got for slides.
And I can just send it to you, but
Okay, so they do talk
so
about
this is
attention.
additive.
Yeah, but it would be good to know what
Oh, okay.
Okay. And did they talk about the multi-head self-attention thing? That is what they called it, right? Did I get that name right? Yeah, multi-head
Yeah,
self-attention.
so no.
Yeah, because that was the thing that I mean, like attention generally I can read up on between now and the next time. The multi-head self-attention, when I Googled it before, I did not find a whole lot. I mean, I did find people using that phrase, but not a whole lot. And so I was just wondering if that was like, something.
So this is I think I just saw something on scalar multiplication. Additive attention, key value pairs.
I mean, I guess there are. If I Googled the exact phrase, it does come up in various places. Although it comes up mostly in like academic papers that are you would think would be kind of above your current pay grade, but it does exist. So.
It wouldn't be so shocking to me if it did come from MIT or something.
Okay. Yeah. So yeah, they may have thrown you some kind of. Let me see exactly what they're asking about multi-head self-attention. I could probably figure this out from academic sources. It just it always is easier if I kind of know like how they were teaching it to you, because like how much they're expecting you to know. All right. So additive attention, that's that one. But then, how many flops does the multi-head?
Oh, so basically, on all this, it was lab stuff.
Okay.
Because this is basically, I can show you word for word from the lab, almost word for word.
Okay.
So we didn't get any taught on this. So we barely did something on the first one, but not the first exercise in this set. So The X1, Y1 stuff, if you remember.
Yeah, kind
That's
of.
the only sort of explanations we got, and they didn't have anything to do with this set. So
Okay. Um, okay. Well, we'll do what we can with it. Did I forget? Did you say you had worked out a way to download these, or are these still not something you can download?
I don't. I'm trying to print them out. I can't. So unless I save them to my OneDrive, I haven't tried that. Um,
Okay, I
my
had a
drive. Let me see if.
shortcut, but yeah, maybe it doesn't let you like. If it doesn't, that's okay. But I was going to say, if it doesn't, maybe what you can do because these sessions are auto recorded.
Yeah.
So you could always just scroll through the whole slideshow just briefly and while with the screen share on and that
Yeah.
and the little like dot 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 menu doesn't have a save option, right? If you
No,
yeah,
just
so,
because it's password protected.
yeah. Okay. Well, yeah, maybe if you just want to kind of, at a moderate speed, just scroll through this whole thing because this will give me something I can look back on if I have time to study up a little bit. It's kind of funny because like when I was a neuroscientist, like attention is one of the main things I studied, but it is quite different when you're talking about attention in the deep learning world. I mean, somewhat similar and inspired, but not exactly the same thing.
Were you working in the Did you have any lab work to do?
Yeah, I mean, I guess we never really talked about this, but I was a professor of psychology and neuroscience for a few years at a couple of different
Oh wow.
places, and yeah, and so I ran my own lab, published papers and all that fun stuff. Can you actually scroll back up a little bit? I saw it kind of the screen share kind of skipped a little bit on.
Oh,
It was that slide with the figure on it, so I just wanted to make sure we didn't lose any of them. Yeah, so I think like right around here it skipped. All right. So I think we got that now. Yeah, I can keep going. I just wanted to make sure
if you
if we
want, I
go
can do
back
like
it
a
would
quick
catch me.
video.
I think this will
Um,
probably catch it. If not, like I said, we have the academic sources. This will help a little bit to know how your professors talked about it. Um,
mhm.
okay, all right. So yeah, all right, cool. That should be helpful. All right, thanks for doing that. And
This might be the only one that was had anything to do with it. If I find something else, I'll
yeah,
just do a quick video and just send it to you.
yeah. Let me know if you do. I mean, that looks like most of it, but yeah, it doesn't look like they cover the multi-head stuff at all. But whatever. Now, when I initially Googled it, I wasn't coming up with much, but I had to when I put quotes around it, I got a little bit more. That's like I said, mostly academic type work. But
Mm-hmm.
we can work it out, I'm sure. Okay, cool. All right. So yes, we probably
Oh,
should.
here it is.
Oh,
Here's the multi-head.
oh, you found another slideshow, you mean?
The actual, it's literally saying multi-head. I
Oh, okay. All right. Is this
can
this
go
is
through this the
another?
same way.
Yeah, let's maybe just do the same thing. Do another. We don't have to spend time on it now, but if you can scroll through it, then that will help.
Here's what you were saying about the concatenation.
Yep.
I searched the word multi-head in this and it didn't find it, so I have no idea.
Yeah. Maybe the text search doesn't work very
Yeah,
well.
maybe.
Okay, yeah, because that does get into self attention. Yeah. Okay. Well, they do. At least they do give you something on this, so that's good.
Yeah.
I mean, whether it's, I'll have to take a closer look at the slides later to figure out if it's understandable, but at least it is not completely coming out of nowhere.
So here's the funny thing. I think it was during one of the labs. I Googled one of the notes, one of the slides. I don't remember which one it was,
Mm-hmm.
and it looked like a literal copy and pasted from a different person. Now
Yeah.
I don't remember where that is. I'll have to look it up. But like the blue and the literally the blue and the white writing and the black and the blue at the bottom.
Yeah, it's possible. I mean, academics,
And there were slides, and
yeah,
yeah.
academics do share these things, but also people just copy stuff, I guess. So, also I guess not really, maybe they copied and maybe somebody copied these slides. I don't, know which direction it would have gone in, but
Oh, it was a
yeah.
different. It was the other way around because this is the first year that this course is being taught. So yeah.
Oh, okay. Well, there you go, I guess. Yeah, because this does
Because
look
last
like.
year was online. Yeah,
Oh, okay. I was gonna
and it
say
was
this stuff
impossible
does.
to do this course online.
Yeah, yeah. This looks pretty advanced for like where you all sound like you should be, but like this seems pretty advanced for kind of like an intro to moderate level course. But whatever, we'll
Mhm.
figure it out. Okay,
Yeah,
cool.
hopefully.
All right. Well, hopefully that all came through in the screen share. If not, I'll let you
If
know.
not,
But
just send me a text and a message, and I'll just do another video myself and just
yeah,
send that to you.
sounds good. All right, cool. So yeah, when did you want to try to meet up again?
Let's do maybe Monday
Okay, yeah.
if
So
you have
Monday.
availability.
Yeah, I've got some. Let's see here. What would work well? Um,
And I do want to set up a 2-hour window, so if you don't have a Monday.
yeah, Monday. I don't quite have 2 hours. I could do like an hour a couple times on Monday, but if you want a 2 hour stretch, um, Tuesday would probably work for that. I don't know if you could do Tuesday
Around
at
what time?
like 1 Pacific would probably be a good time, or a little bit after that.
Okay.
Does that
Yeah, let's
work?
just do 1 Pacific. Yeah.
Okay. All right. So yeah, I've got a good 2 hour stretch there, and that's actually got a little bit of room after 1 Pacific, or after 3 Pacific. So if we needed to even run a little bit longer than that, we could.
Okay.
But okay, cool. So yeah, I will set that up, and we can plan on that.
Awesome. Sounds
All
great.
right, cool. Anything else for today, or is that everything for the moment?
I think that's everything. Let me just do something real quick. The chat, it doesn't save in the
Oh yeah,
what's it
I can
called?
copy those links and like put them in a text document or something if you want, or
Oh, yes, please.
yeah. Let me
I
just
was just
copy
saying it
that.
doesn't copy in the Wisent board, right?
Yeah,
The
good
zip file.
point. Yeah, when you save the whiteboard, it doesn't save those. So yeah, when I send you the whiteboard copy, I will also send you these links. Let me
Okay.
just get all 5 of them copied. Yeah, I
Mhm.
usually don't worry too much about the chat links, because I figure like I can always go back in my history or whatever. But these particular ones were probably a good set to save. So, all right, yeah, all right. I think I've got all 5 of those. 2, 3, 4, 5. Yeah. All right, cool. So I will send you those and the whiteboards as soon as we log off here.
Awesome. Thank you so much.
All right, thanks. I'll see you on Tuesday at what did I say?
See you on
1
Tuesday.
Pacific. Yeah. All right, thanks. See you then.
Thank you. You too. Bye.
Bye.